Welcome to the Deep Dive, where we unpack complex topics from your sources to give you the essential insights. Today, we're diving into the fascinating world of prognostics and health management, or PHM. You sent us some really robust research here, and our mission today is, well, to cut through the density and reveal how PHM is quietly revolutionizing things. Everything from giant power plants right down to the engine in your car.
It really is. It's a cornerstone of the fourth industrial revolution,
Yeah.
aiming to integrate digital intelligence, physical machinery, and, importantly, human expertise. We call them socio-cyber-physical systems. Sounds complicated, but at its core, PHM is just about anticipating problems before they happen.
Right, not just reacting when something breaks down.
Exactly. Imagine predicting the future health of a machine. Could be a tiny component, could be a whole system.
That's the goal, isn't it? Moving away from that reactive firefighting mode to something, well, more proactive and optimized.
Yeah, just in time, just right, maintenance. That's the promise. Maximize profits/unexpected failures. Sounds great.
But like any big technological leap, getting there isn't exactly straightforward. So what are the biggest roadblocks right now? What's holding back full PHM deployment?
Well, the sources point to challenges in sort of three main buckets. First, the actual physical degradation. How things wear out is inherently complex. Second, the data itself. What we have, what we don't have. And third, the demands we put on the solutions.
Okay, let's talk data first. That always seems to be a hurdle with AI.
Oh, it's a minefield. Seriously.
Yeah.
You've got anomalies like missing sensor readings or just plain wrong ones. Then there's the scarcity of labeled degradation patterns. I mean, thankfully, serious faults are rare, right?
Yeah.
But that makes them super hard for AI to learn from.
Because it hasn't seen enough examples.
Exactly. Plus, you have the sheer volume and variety of data, the whole big data thing. And machines don't operate in a vacuum. Their conditions are always changing. All of this can really mess with the models.
Okay, so data's messy. What about the demands? You mentioned it's not just about getting the right answer.
Right. Beyond just pure accuracy, which is obviously crucial, there's this growing demand for interpretability.
Meaning you need to understand why the AI made a certain prediction.
Precisely. You can't just have a black box spitting out answers, especially in critical systems.
Yeah.
You need to trust it. And that means understanding its reasoning. And, of course, security. These systems manage vital infrastructure sometimes, so robust security is absolutely non-negotiable.
These challenges definitely sound significant. But the exciting part is always the innovation, right? How are researchers and engineers actually, pushing back against these limits?
Absolutely. Let's look at fault detection first, just spotting that something's wrong. Here, methods like generative adversarial networks, GANs, are proving really effective, especially when you don't have much fault data.
How do they work?
Well, instead of learning what faults look like, they get incredibly good at learning what normal looks like. Really, really good. So the clever part is, anything that deviates from that learned normal immediately flags up as an anomaly, even if it's a type of fault the system has never encountered before.
Ah, that's smart. Flip the problem.
Exactly. And another exciting area is optimal transport methods. Think of comparing complex data patterns like vibration signals. These methods let you compare the raw shapes of the data directly without needing lots of assumptions. Gives you great sensitivity to subtle changes.
Okay, so we've spotted something's off. How do we figure out what it is? Diagnose the actual problem-bearing valve.
Right, that's fault diagnostics, pinpointing the type and cause. And again, the big hurdle is often that missing labeled data. Here, something called reservoir computing, specifically using conceptors, is showing real promise.
Reservoir computing.
Yeah, think of it like a type of neural network that's really good at handling data that unfolds over time, even irregularly. It can pick up on these long-term patterns, these sort of temporal dependencies. Conceptors kind of act like filters within that system to specifically capture different degradation signatures, even from limited examples.
Okay, and the crystal ball part. Predicting how much life is left. The RUL.
Yes, failure prognostics, predicting remaining useful life. A big challenge there is dealing with event-based measurements. Data that doesn't come in a nice, steady stream, but maybe only when something specific happens, like an alarm triggers.
Irregular data.
Right. So echo-state networks, ESNs, are being developed to tackle this. They can predict the RUL directly from these fragmented clues. They effectively learn to sort of fill in the blanks without needing us to manually reconstruct all the missing data points first.
That brings us back to something critical you mentioned earlier. Interpretability. Why is that so vital? It's not just academic, right?
Absolutely not.
Yep.
In safety-critical applications, think nuclear power plants, aircraft engines, it is simply not enough for an AI model to be accurate. You must understand how it reached its conclusion, period. It's fundamental for trust, for safety, for accountability.
So how do you make these complex AI models explain themselves?
Well, there are techniques. One is called LIME, Local Interpretable Model Explanation. Think of it like getting a specific explanation for one particular prediction. It tells you which input features were most important for that specific decision. Like, it predicted failure because sensor X showed this spike.
Okay, that makes sense. Focused explanation.
Yeah. And another approach is using ALE plots, accumulated local effect plots. These help you visualize the overall impact of a feature on the model's output, even when features are correlated, which happens all the time in the real world. They help us really dig in, question the model's assumptions, and understand the sort of causality it has learned.
So pulling this all together, what's the big picture takeaway for us, for the learners listening?
I think the key thing is that PHM isn't just about fancy algorithms fixing machines. It's really about making the systems we rely on, industrial, infrastructural, safer, much more efficient, and more reliable. And it does this by merging deep engineering know-how, that domain expertise, with these advanced AI techniques. The challenges are definitely real, but the innovation is tackling them piece by piece.
It really makes you wonder, doesn't it? If we can get this good at predicting the health of a complex machine like a turbine, what else could benefit? What other complex systems in your life or work, maybe even non-mechanical ones, could use this kind of prognostics and health management? How might thinking about these concepts, dealing with messy data, needing interpretability, change how you approach problem solving? Definitely something to mull over until our next deep dive.